So we're going to talk about some considerations to choose tubing size. And by size here, we're referring mainly to the diameter, because in most cases, like for example, due to the depth of the formation of the reservoir where you want to produce from, then there is not much flexibility there. You are already bound to have some length, the tubing will have certain length. Okay, so it's tubing size considerations. Okay, as I mentioned, is not a cookbook to tell you how to choose tubing, but some things that should be taken into account when choosing tubing diameter. So the first one is that here is mainly diameter. Okay. So one of the main objectives is to maximize Q oil and Q gas. You want to increase as much as possible the rate of oil and the rate of gas. And that is simply to increase the equilibrium rate. Okay, so if we have our system of our layout of one well, we have PR, PWF, then here we have our Christmas tree. Let's assume that we are very close to a separator, okay, such that we can say that P wellhead is equal to P separator. Okay, then if we do downhole equilibrium, QG for example, so we know one part of that is going to be representing the formation, is going to be the IPR. And another part of that system is going to be the TPR. Okay, and typically this TPR is calculated with some diameter, okay, let's say phi1. So what happens when we increase the diameter, usually the intersection here is just moves to the right. Let's say for another diameter, the origin is going to be the same because the diameter doesn't affect usually the hydrostatic part in which you have no rate. But if you, let's say, increase the diameter, then you get an intersection and you increase the rate. Okay, or also the opposite. So if you reduce the diameter, then you're going to have an intersection which is here. So this is the at phi 3. Okay, and this direction here, it's saying, well, phi is increasing. And you see, for example, let's paint just one more. Okay, which might be something like that. Okay, so you see, for example, that there is a big change in the equilibrium rate between this one and this one. Okay, this is QG star, and this will be for 3, and this is QG star, and this will be for 2. But then, for example, there is not much difference between this one, which will be phi 4. Okay, between these two, there is not much difference. Okay, and that takes us to the second point, which is that you want to minimize cost. Okay, you always want to maximize. That means you want to maximize revenue. Okay, ultimately what you're trying to do is maximize revenue. Okay, but at the same time you want to minimize cost. Okay, so you have to put these two things in a balance to see how much is it costing and how much you're getting out of it to decide which size you should use. Okay, and in some cases, like, you have to be very careful because some cases like this one, really changing the tubing diameter doesn't give you much more. Okay, while for here, between here and here, it gives you a lot more. And then it's not worthwhile the additional cost. Okay, so in this case, the lower the diameter, the lower the cost, typically. So one thing we should point out is that you cannot, so tubing is made out of pipe sections, okay, so it's some section of some length, okay, and you thread them together. Either I will show you soon, but either they come with a thread. Okay, these come with a thread, for example, internal and external, or you do it using coupling. But it's not. But the tubing usually comes in discrete sizes. Tubing comes in discrete sizes. Okay, it's not that you can have any continuous value for phi, but actually you have only a series of diameters that you can use. Again, as an example, I'm going to show you it's a tubing table. So there is tubing according to API. Remember, API is the American Petroleum Institute. Specs. Again, here there is a table. Took it from a website called oilproduction.net. Okay, you see these are all the sizes available, and typically this is the outer diameter of the pipe. Okay, not in this case. Yeah, here it starts to be the outer diameter. Okay, not on the rest. Okay, but you see you have the diameter, and then you have, depending on the grade, which the grade tells you is like the type of steel, and this number usually is the resistance of the steel in 1000 psi. And it also tells you something about the properties of the steel, the resistance to corrosion, etc. And then you have here the inside diameter. Okay, so it's not that you can have any number between these two, but you can have either this one or you can have either this one. Okay, when you go and increase the size, you have some more options for different tubings, and these are usually quite popular for onshore wells. Yeah, and you go in the API table, you go to 4.5. So when you're choosing tubing size, just remember you have to first also be sure that you are for the application you have. You first have to look at the grade, at the resistance, okay, depending on the pressure rating that you need, and also the compatibility with the fluids you're using, and then based on that you look at the inside diameter. Okay, that's great. So this is according to API, but you can also have non-API tubulars. Okay, we call typically so tubing, because it can be also tubing and casing, so we call these tubulars. And I'm going to show here one which is from a company called Valorec. Okay, this is they have a line of products called VAM, and this is a French company. You see here they have the name Smart Tubular Solutions. And you see the sizes they have available. Of course, they have different products and they have different, these are all the products they have, and they, depending on the type of thread, depending on the connection, depending on the properties, but these are all the sizes they have. Okay, you see all the way to 26. So these are a non-API, and you can see they can go much bigger sizes. And of course, when you go above, like 9 inches, something like that, then it will be casing. And even you have also, for example, riser. Okay, this goes all the way to 26. Okay, and they're going to have a different internal diameter, and actually this internal diameter is the one that is used in pipe flow calculations. Okay, and from some point here, probably this all will be for tubing. Then from some point here, this will be for casing. And from some point down here, this will be for riser and flow line. Okay. So in my compendium, I have, so how do we usually name or how do we usually tag tubing? We use the following four elements. So we have first one is the size of the tubing. Then we have this is the weight per length, how much it weighs per length. This is usually in pound per foot. And then this is the grade. In this case, this is the resistance, okay, of the material in the yield strength in 1000 psi. And this is the type of thread. We are not going to go too much into that part, but each tubing have a different way that they make the thread. Okay, so this is some different types of thread. Okay, but that's how we address, we usually call the tubing. This is how we, the tag of the tubing, the specs of the tubing. Okay, so this is referring to the size, and this is typically called the nominal size. This is the weight per length. Okay, and this is in pound per foot. Okay, usually you see the abbreviation ppf, and this is the steel type. Okay, or we can call it grade, or we can call it as resistance. And this one here is the type of thread that we're not going to talk too much, but to join these tubings, let me here I think I have an image. Okay, you can join tubing in different ways. Okay, you have here, for example, this is the one to the left is called an integrated joint, in which part of the tubing is male, or they call it pin, and part of the tubing is female, or is a box, and then you screw them together. Okay, they are threaded together. While you have in this case this other option in which both ends of the tubing are pin. Okay, and then you have a coupling, which is the box. Okay, these are two types of connection, but this is not what this part refers to. This refers more to the type of thread that you have on the tubing. Okay, but this is what we call a coupling. Okay, I think I have the name here. Let me make sure. Okay, coupling or integrated joint. This is an integrated joint, and this is with coupling. Okay, and for the cases of this integrated joint, you have some cases in which it's protruding on the inside. It doesn't have the same diameter, but when you come to the joint, then you're going to have a reduction in diameter. For example, it could be something like that, or it could be that inside it allows full pass. You don't have any restriction, but then it's bulking out, it's protruding on the outside. Okay, so then you have different nomenclature how to refer to those type of connection. Let me find, I think I have, the coupling is usually mounted. Okay, here's a machine that is used in the to connect the coupling to the tubing. In this case, this is not tubing, but it's a casing. Okay, you see how the coupling is being threaded into the casing. I'm going to put the link to the video. Maybe you can put it here. Okay. So just be careful. So the whole discussion was to say, well, be careful to what, when deciding on sizes, you can, from this analysis, say approximately what kind of ID you need. Okay, and then after you have the ID, well, you have to come to these tables, and then you have to pick the one that is the closest. Okay, taking into account the grade of the steel, taking into account the size, taking into account if there's going to be an API or not. So it's a lot of things to take into account. Okay, and you know how to ask, roughly how to ask for tubing. Another consideration we have to make when something else that we have to consider when picking tubing size is related to the tubing hanger. Okay, so if you remember, let's make our completion or our well diagram schematic um, a bit more detailed. Okay, remember that I told you we have our tubing. Okay, and then we are hanging that with some sort of a disc. Okay, this is what we call the tubing hanger. And this tubing hanger is not only holding the tubing typically. So first, this, the production casing. This usually these diameters. Okay, so this is 9 and 5/8 inch. So you should fit usually that. And sometimes you have inside a liner. So there are some cases where a, for example, here you have a liner which is of smaller size. Okay, so so then if you want, maybe you want your tubing to go inside. I don't know, not very common, but might be a case. Okay, so always be careful that you're going to put your tubing string inside another string, and that will, of course, then it has to be smaller than that string. Okay, but something more important is that typically you don't have only the tubing, but for example, you have a pressure gauge, which is here. Okay, at the downhole. This is a downhole pressure gauge. Okay, and then you have to send the signal there, you have to make a hole through this tubing hanger, and then you have to pass the line. Okay, in this case an electric signal, the electric signal, you have to pass it through some cable. Okay, and also to avoid that you will have damage, typically you have some sort of a clamp. Okay, you may have also other things. You might have maybe downhole. You have, for example, some kind of inflow control. Okay, something that regulates. Let's say um, you might have other line. For example, you have a electric submersible pump, ESP. Okay, and then you have to put the cable, which is a power. This is a power and signals. Okay, you sometimes, in some cases, offshore wells, they have, uh, because usually to have access to the annulus, you can do two things. So you can have a valve here, okay, in which you have access to the annulus, okay, but another option is that you put a piece of pipe, and this will be the annulus, the access to the annulus, okay, so this could be um, a few meters, a few hundred meters in length. Okay. Another thing which is very important, this is something that could be optional. Some wells could have it, some wells could not have it. Onshore wells, they seldom have downhole pressure gauge. Okay, but if you have ESP, then this is a more typical case if your well is ESP lifted. But one thing that almost every well has, or I think almost every well has, is this downhole safety valve. Downhole safety valve. Okay, and typically you need is a line, which is a hydraulic line, to keep it open. Okay, and we're going to see we have one of those in our department. So this is a piece of this downhole safety valve. If you have your tubing, so then it's threaded into the tubing, and then it continues with the rest of the tubing down. So this part is the downhole safety valve. Again, we have some how it looks like. This is the bottom part, which is here is going to the reservoir. Okay, you see here, very important, you see they have this flapper, okay, which in this case is closed. So in this case is in the safety position that it doesn't allow any fluid to flow towards the surface. Okay, and this part you will see now what moves, but what moves is this. If you see here is like a piece of pipe inside the valve, okay, which is pushing the flapper. When this one is extended, it's going to be pushing the flapper against the wall, and then the valve is going to be open. And what is pushing, trying to keep it closed, is this spring. Okay, so when there is no hydraulic force, here is the hydraulic piston that I was using to put force and to counteract the spring. Okay, you're going to see now very quickly one animating this. And then you have that spring which is pushing, is holding here and pushing this one up. Okay, so it's pushing this inner pipe up. And here are the cylinders that these are activated. These get hydraulic fluid from the surface, and these are pushing to counteract the spring. Okay, and you see maybe up here, you see this capillary tubes, the hydraulic line, that this is the one that is going to be, that we specified here on our drawing. Okay, which is, it will be this green one here. Okay, and this also have to be clamped, okay, because you don't want it to get damaged when you run it in the hole. Okay, so they have to be clamped. I think I have a picture of a clamp here. Okay, you see that's the clamp. This is not for that, not for this cable, but this is for ESP clamp. But still, you get the point. You get the idea how it is. Sorry, I don't remember where. I think I took it from Google, this image. Okay, so this is this clamp that you have here. We just put asterisk and then, okay, that's a clamp, and this is for ESP, because the ESP cable is typically like rectangular. Okay, so you see here that this part is kind of rectangular. Okay, this is what's holding against the pipe. So let's see the video of the one operating. Okay, so now I'm pushing. So you see this whole thing is going down and is pushing against the spring. Okay, here I'm pumping it, and you see that it's covering the cylinder, is covering the flapper, and also it's going to be protecting it, because when I have flow here, I don't want to have any erosion on the flapper, because the flapper is what actually makes the seal. Okay, so it's on this position that is normally the hydraulic line is acting and everything is is acting all the time. But when something happens in the surface, let's say you have a fire, you have some safety problem, or something happens that you miss the hydraulic fluid, then what happens is as the spring is going to be more powerful than the hydraulic line, and then it's going to close. Again, this is something that you always need in case of safety, because otherwise, if something happens to the wellhead, something happens to the Christmas tree that you cannot control anymore the well, then you don't have any barriers. So then in that case, you will have simply, the hydrocarbon will flow to the surface, and then you have an uncontrolled burning of the fluids. Okay, this happened. You can see some images of I think in the Kuwait Gulf War, I think they have some images of that. Okay, you have some images. In that case, I don't know exactly the details, but I think they were bombing parts of oil fields, and then you see, because the Christmas tree is gone, then you have no control on the well, and then you start burning without any control. Okay, so for that reason, it's very important to have this downhole safety valve that that allows, it's due to safety, impedes for the fluid to flow out. Okay, so all of that discussion, sorry we took a bit of a detour, but all of that discussion is to say that the tubing hanger, if you see it from the top, typically has just the hole for the tubing, but also might have a hole for the annulus, then has a hole for the electric cable. Okay, you might have another hole which is for downhole pressure gauge. Okay, what else did we say here? Uh, you have one which is for the downhole safety valve. Okay, then you might have also chemical injection. Okay, you also have maybe someplace here at the bottom, you have something that is a scaling inhibitor to inject scale inhibitor or to inject wax inhibitor, for example. And then you also have to send that to surface. You might have also inflow control. You have a valve, a downhole valve. This they call an inflow control valve. Okay, and then you need also a hydraulic line to activate or deactivate. So the point is that you need to have enough space to um, uh, it's like you need to have enough space. If you have a lot of holes here, then the structural property is going to be weak, okay, and it's not going to be able to carry the load. Remember, the main purpose of the tubing hanger is essentially to carry the load of the tubing, okay, is laying that load on the production casing. Okay, so it should be able to transfer the load from the tubing, which is quite a lot of strings, 2 kilometers, 3 kilometers of steel, okay, that it has to carry, and that one has to be transferred to this one. So it has to be very structurally solid, okay. Okay, so if you have a lot of holes, then that means that you're making it weak, okay, and it won't be able to, it will be, you cannot make that many holes because then it won't have a structural strength to carry the weight of all the tubing. Okay, and here is one case. This is with the ESP cable, ESP cable. Okay, you see the cable, you see a bit better image of the tubing hanger, okay, which is this part here. You see here, this is the shoulder, okay, that I make it very exaggerated. Okay, here on this drawing, I make it very, very exaggerated, but actually it's not that big. Okay, here you can see it's actually quite mild. Then you have a seal, which avoids fluid from here to go up. And there you have this port, and this typically we call is like a penetrator. Okay, that we go through the tubing hanger, and here of course we have the tubing. Okay, you can see this takes a considerable space in the tubing hanger. I have an image on my compendium, a sketch. Um, let's see if I find it very quickly. Okay, this is the wellhead. Okay, so then you can see the tubing hanger. You see threaded to the tubing is threaded to the tubing hanger, and here you have a line which can be for example, for the downhole safety valve. Okay, and this number of pores you have and the space you have is limited in the tubing hanger. So you also that's something that we should take into account. Okay, maybe we cannot go that high. We would like to have a very big tubing, but we cannot go that high because actually the well has a lot of things inside that we have to that we have to have lines for. Okay, and here you see this the shoulder is a bit bigger, okay, but it's the same, it's not that big as I put it on my sketch.